In section 7.2, we are going to talk about some more identities, and I'm going to try to explain to you where some of these identities come from. So hopefully they're a little bit more understandable and not just some random formulas that you need to remember. And then also show you a couple things that we can do with them and work out some simplification problems that use them. So 7.2. We are doing cofunction identities, double angle identities, and half angle identities. So 3 different types of identities. But we're going to work off some of the ones that we already know to help us figure out some of these new identities. So I'm going to start with the cofunction identities. And we've talked about cofunctions already back in chapter 6 a little bit. So let's start with the cofunctions. And cofunctions are 2 trig functions that have the same value when we plug in angles that are complementary. So complementary means they add to 90 degrees. So x plus y equals 90 degrees. Now in this section, they use radians. So instead of 90 degrees, you're going to see pi over 2 in the identity instead of 90. So some cofunction identities that we see, and you could also see this just from your unit circle, sine and cosine share a lot of the same values when the angles add up to 90. Tangent and cotangent are cofunctions, and you'll also see if you look at the actual names of the trig functions, the names are the same except one of them has the word co in front of it. So sine and cosine, those are cofunctions. They share the same set of values, and their values match when the angles add up to 90. Tangent and cotangent. Secant and cosecant. One thing that I've noticed on some of your tests is you're getting these abbreviations wrong. So it looks like you know how to do the values, but you're just getting some of these mixed up. Sine is sin, cosine is cos, tangent is tan, cotangent is cot, secant is sec. So far, all 5 of those trig functions have just used the first 3 letters of their name. For cosecant, this is our one oddball where we can't do that. We can't use the first 3 letters because we've already used cos for cosine. So cosecant is the only trig function where we don't use the first 3 letters as the abbreviation. So cosecant is CSC. So just be careful with that. Cosecant is CSC. So these are the cofunction relationships. It's really just the same word with a co in front of it. So our cofunction relationships, if we write this out as an algebraic formula, the sine of some value is going to be exactly the same as the cosine of whatever pi over 2 minus that value is. or 90 degrees minus that value. Pi over 2 and 90, pi over 2 radians is the same as 90 degrees. So the way that this works, I said if the angles add up to 90 or pi over 2, then the trig functions would be the same. So the sine of 20 degrees is the same thing as, well, if I put 20 in right here, 90 minus 20 is 70. Sine of 20 is the same as cosine of 70. Those two values are exactly the same. And you could check it on your calculators, just make sure you're in degree mode. So this formula just ensures that we're working with a complementary angle. And it would also work if we were doing radians, we would just use pi over 2 instead of 90. So our co-function identities, and this is the same for all of the other pairings, the actual identities are sine of x equals cosine of pi over 2 minus x. And it really doesn't matter which side we write either one of them on. So we could interchange them and say cosine x equals sine of pi over 2 minus x. We could write it either way. It works both ways. We could also write the same exact thing for the pairing between tangent and cotangent. So tangent of x equals cotangent of pi over 2 minus x, or flip-flop them, cotangent of x equals tangent of pi over 2 minus x. And then our other cofunction pairing is secant and cosecant. So secant x equals cosecant of pi over 2 minus x, and flip-flop them, cosecant of x equals secant of pi over 2 minus x. So those are our co-function identities. And the trick is to remember that the angles are going to be complementary. Co-functions are for complementary. Both of those words start with CO. And then also to decide what functions to match up, we just insert a CO or remove a CO from in front of the trig function. So to figure out what the co-function is for sine, just put a co in front of it, cosine. To figure out what function is a co-function with cotangent, it already has a co, so remove it. It's going to be tangent. Those are co-functions. Now there are some other trig identities that involve pi over 2, but these have a plus in them instead. And to deal with those, what I suggest you do is your sum and difference formulas that you learned back in the last section. And I will show you how we can simplify them with the sum and difference formulas. So some other identities that involve pi over 2. So we could have the sine of x either plus or minus. And I'm going to do these in two different colors. This could come out two different ways. I'm just either adding or subtracting inside of the angle. So back in section 1, we learned a sum and difference formula, a sum or difference formula for sine. So I'm just going to use the sum and difference formula to expand this. And that sum or difference formula says you're going to do the sine of the first angle times the cosine of the second angle. And then you're going to use the same exact sign that you have in the middle. And then you're going to flip-flop. You're going to do the cosine of the first angle and the sine of the second angle. Now, one of these angles is x, so we're not going to be able to figure that one out. But the other one is pi over 2. We can figure that one out using our unit circle. Cosine at pi over 2 is 0. So anything times 0 is 0. This whole first piece is going to go away. Sine of pi over 2 is 1. Anything times 1 is equal to itself, which means the sine of x plus or minus pi over 2 is equal to plus or minus cosine x. So your sine stays exactly the same. It just turns into cosine. If it's plus inside, it's positive cosine. If it's negative inside or subtraction inside, it's negative cosine. And I figured that out just using my sum or difference formula back from section 1. So this is technically another identity that involves pi over 2. It's not necessarily the cofunction identity because these angles don't necessarily add up to 90. They involve 90 degrees. They involve pi over 2, but they don't necessarily add up to 90 because the way that expression is written. But you can just use anytime there's addition or subtraction inside that angle, we can refer back to that sum or difference identity to help us simplify it. And I'm going to do the exact same thing for cosine of x plus or minus pi over 2. I'm just going to expand this using my sum and difference formula. Now the formula for sum and difference on cosine is completely different. And the way that I like to explain it, and if you watched my video for section 1, you might remember, sine is the nice guy. He likes to share. So that's why we did sine and cosine in the first term and sine and cosine in the second term. He likes to mingle, he likes to share, and he keeps the same sign. He doesn't switch the sign on you. If it's plus here, it's plus here. If it's minus here, it's minus here. Cosine's exact opposite. He's mean, he's greedy, and he doesn't like to share. He's going to change the sign on you. So cosine is going to go ahead and take both of those angles to start with. So we're going to have cosine x, cosine pi over 2. So he's greedy. He's going to take them both. And then he's going to switch the sign on you. So if your problem had a plus in it, he's going to change it to a minus. If your problem had a minus in it, he's going to change it to a plus. And then once he's had his turn with both of the angles, then he's going to let sine have a turn with both of the angles. And the pieces that have the pi over 2s we can simplify. Now earlier we said cosine of pi over 2 is just equal to 0. Sine of pi over 2 is equal to 1. So anything times 0, that whole piece is going to be gone. And then anything times 1 is just going to be itself. So we end up with cosine plus or minus pi over 2 is equal to either negative or positive, sine x. So with the sine, it stays exactly the same, but with the cosine, it changes. A plus turns into a negative answer, a minus turns into a positive answer. And all of this is just because our sum and difference formula. So it follows the same pattern as the sum and difference formula. In the sum and difference formula for sine, the signs stay the same. In the sum and difference formula for cosine, the signs change. Same exact thing here. So that's just a little quick way to remember what's going on with these identities. For the double angle identities, I again am going to refer back to the sum and difference identities to help remember these. So for double angle identities, you should always think about using double angle identities. Double angle, if you think about what exactly that means, double means times 2, and it's inside the angle. So double angle identity, you should probably be using anytime your angle is being multiplied by 2. So we've got a double angle identity for sine 2x, cosine 2x, tan 2x. And I'm going to write these out, but I'm going to show you why they work based on stuff that we've already learned. Sine 2x is equal to 2 sine x cosine x. Now you can't just say, well, I'm going to take the sine value and I'm going to double it. I'm not doubling the sine value, I'm doubling the angle. I'm not doubling the sine value. If that was the case, I would have my 2 in the front. What I'm wanting to do is I'm wanting to double my angle. And that's something completely different. And it gives a completely different answer. So if we don't know what that angle is, then we won't know how to double it. So what we need to do is we need to revert this back to something in terms of the original angle so that we can figure out how to do this. So we use an identity to revert it back to the original angle. So sine 2x, in order to revert this back to the original angle, we say, well, that's equivalent to 2 times sine x times cosine x. And I'm going to show you how to figure that out using the sum and difference identity in just a minute. Now, cosine 2x actually has 3 different options on things that you can use for its identity. It depends on what situation you're in and what's going to be most convenient. So cosine 2x, you can either use cosine squared minus sine squared. That's taking something that has a double angle and reverting it back to the single angle. So that's an option. But you can also use 2 cosine squared x minus 1 or 1 minus 2 sine squared x. All 3 of those are equal to cosine of 2x. So again, depending on the situation that you're in and what exactly you're trying to do, all 3 of them will work. You've got 3 options here. A lot of times, we'll just use one of those because they only have one trig function in them. Usually when we're trying to simplify a trig expression, it's simpler to only have one trig function in the problem rather than 2. And that first option has 2 different trig functions in it. So cosine 2x has 3 different options. And then tan 2x is 2 tan x over 1 minus tan squared x. Now I'm going to show you how I get sine 2x. And if you want to, you can repeat this process for the other ones as well. But I don't want this video to get too crazy. I still want to go through a bunch of examples with you, besides just showing you how to derive these formulas. But I want to show you how you can come up with that identity without necessarily having to memorize it. So sine of 2x. You could technically think of 2x as being x plus x. X plus x is 2x. Algebraically, that is completely correct. And if we write it this way, we can use our sum and difference formula on it. So again, I'm going back to something that we've already learned in section 7.1, and I'm going to apply the sum and difference formula, but both of my angles here are x. So the sum and difference formula for sine says we let sine use the first and let cosine use the second. Keep the same operation and then let cosine use the first and sine use the second. What looks a little bit confusing though is that both the angles are the same, so everything says x. These are like terms. They both have a sine x and a cosine x. So technically, we have two sine x, cosine x. That's the exact identity I just wrote up here. 2 sine x, cosine x. And we could do the exact same thing for all of these. We could write 2x as x plus x, and we can just go through our sum and difference formula and prove that these are true. Now, to prove those other two cosine 2x formulas, we would also have to use some Pythagorean identities, but you could at least show that that first one works. And maybe I'll show one of these others works in one of my examples here in just a minute. But before we go through any examples, I want to show you the last set of identities here in this section, which are the half angle identities, which tend to give people the most trouble. The half angle identities are when you're trying to find the value, the exact value of an angle that got cut in half. And again, you cannot just take the sine value and cut it in half. That's not what it's asking us to do. It's trying to ask us for the exact value of an angle that got cut in half. So for the sine value of an angle that got cut in half, it's either positive or negative square root of 1 minus cosine of x over 2. Now, one of the things that a lot of people get wrong is when they actually use this formula to do a calculation, they put plus or minus in their answer, and that's not correct. You've got to decide whether your answer should be positive or negative based on what quadrant your angle's in. Your answer should be either positive or it should be negative. Sine is positive in quadrant 1 and quadrant 2. Sine is negative in quadrant 3 or quadrant 4. You've got to decide. So if you're actually using this formula to do a calculation, don't put plus minus in front. You've actually got to decide if it's going to be positive or if it's going to be negative. And that's true for all of these half angle identities. They all have a plus minus in front. And you've got to decide if it's one or the other. The cosine of x over 2 looks very, very similar. There's only one tiny difference. Oops, sorry. Cosine of x over 2 is positive or negative based on the quadrant. Cosine is positive in quadrant 1 and quadrant 4, and it's negative in quadrant 2 and quadrant 3, and you can look on your unit circle and verify that. Cosine of x over 2 is 1 plus cosine of x all over 2. So the way that I remember this is both of these contain 1 and cosine and divided by 2. The only difference is one of them has subtraction and one of them has addition. So the one where the trig function stays the same, I've got positive. The one where I'm changing the trig function, it's negative. So my half angle identity always has cosine. But if I've got to change it to cosine, I'm going to put minus. If I'm keeping it cosine, it's plus. That might not be helpful to you, but that's how I've been able to remember whether it's supposed to be minus or plus. If I've got to change it from sine to cosine, then it's going to be subtraction. If I get to keep it cosine to cosine, it's going to be plus. Everything else about this formula is exactly the same. And then tangent of x over 2 has got multiple options. Just like with our double angle identities, cosine of 2x had multiple options. Tangent of x over 2 has multiple options. So there's one with plus minus square roots. And really, the first option is just the sine formula divided by the cosine formula simplified. So it's 1 minus cosine x divided by 1 plus cosine x. So if you were to take our previous sine and cosine formulas and divide them and simplify, those divide by 2's would cancel, and you'd be left with the sine numerator in the top and the cosine's numerator in the bottom because of the division. But there's two other options for the tan of x over 2. You could also do sine of x over 1 plus cosine x, or 1 minus cosine x over sine x. You've got three options. And if I were you, and you had to do a tan x over 2 value, I would avoid the one that has the square root in it. Unless I was specifically told I had to use that problem, I would certainly use the ones that did not have a square root in it. I would not make this problem harder for myself than I needed to. So I would use either the second or the third because they don't have the plus minus square roots in them. They look easier to evaluate. So we've got three different options for tan of x over 2. We could use any of those three and they would all give us the correct answer. So these are all of the identities in section 2. And what I want to do now is go through some problems to show you why we would want to know these identities and what we would use them for. So we are going to find, the exact values of sine 2 theta, cosine 2 theta, and tangent 2 theta, given cosine theta equals -3/5 in quadrant 3. So we know a little bit about the original angle and what quadrant we're working in, and we want to know what's going on with the trig values of double that angle. You can't just take that -3/5 and double it. That's not what they're asking us to do. They're asking us to double the angle, not the trig value. What happens when you double the angle? So there's a way to use an identity and put this back in terms of the original angle. In quadrant 3, what I suggest you do is you draw a triangle. In quadrant 3, our angle is going to look something like that. And when we connect this back up to the x-axis, we'll have our reference triangle. Cosine is adjacent over hypotenuse. So our adjacent side is -3. Our hypotenuse is 5. And we can use the Pythagorean theorem to figure out that opposite side. And we're going to need to know that because to figure out sine of 2 theta, the formula, the identity, is 2 sine theta cosine theta. To figure out that value, I need to know what sine of theta is and cosine of theta is. Now, we already know cosine of theta. They gave us that value in the problem, but we don't know sine theta. And we can't figure out sine theta unless we know what the opposite side of that triangle is. So I'm going to use the Pythagorean theorem to figure out what the opposite side of that triangle is. And you need to be careful because we're working in quadrant 3, that opposite side of the triangle is going to have a negative value. Everything in quadrant 3, all those sides are negative. It's a negative x and a negative y. So negative 3 squared plus b squared equals 5 squared. So that's 9 plus b squared equals 25. So b squared ends up being 16, which means b could be either positive or negative 4. And we're going to use negative 4 because we're down in quadrant 3. That is enough information to now work all of these problems. So for sine 2 theta, we need to do 2 times the sine of theta. Sine is opposite over hypotenuse, so negative 4/5, times cosine theta, which is adjacent over hypotenuse, which is negative 3/5. And multiply it all together. Sine of 2 theta equals 24 over 25. Because we got a double negative, they will cancel each other out. 24 over 25. They also want to know cosine 2 theta. We've got 3 different identities for cosine 2 theta. So let me go back up here again real quick. We can use any of these for cosine 2 theta. So it might be easier to just use one of the formulas that only has one trig function in. I'm going to use this one because they gave us the cosine value. So 2 cosine squared x minus 1. You really could use any of those 3 formulas and you will get it right. But for just my personal opinion, I'm going to use 2 cosine squared theta minus 1. They told us in the problem, cosine of theta is negative 3/5. So this is going to be 2 times negative 3/5 squared minus 1. So 2 times 9/25 minus 1. That's 18/25 minus 1, which is, I'm going to write my final answer down here. Cosine of 2 theta is negative 7/25. And then finally, we want tan of 2 theta, and we will have to refer back to the triangle for this one because tan of 2 theta needs the tangent values, which are opposite over adjacent. So we'll look at our triangle for those. Tan of 2 theta is 2 tan theta over 1 minus tan squared theta. So tan is opposite over adjacent. Negative 4 over negative 3, but it's a double negative, so it's going to change to positive 4/3. So 2 times 4/3 over 1 minus 4/3 squared. And we need to simplify that as much as possible. So that's 8/3 on the top and 1 minus 16/9 on the bottom. So 8/3 on the top. And that is going to be negative 7/9 on the bottom. And if we flip and multiply, let's see, it's going to be 72 over 21, but that can simplify to negative 24 over 7, I believe. Yep, negative 24 over 7. Tan of 2 theta equals negative 24 over 7. This is enough information to figure out what quadrant 2 theta is in. All we have to do is look at the signs of those answers and we can figure out what quadrant 2 theta is in. So the sine value is positive. Remember, sine is positive in quadrant 1 and quadrant 2. So already this narrows us down to Q1 and Q2 because sine came out positive. When we did cosine, we got a negative. Well, cosine is negative in quadrant 2. Can't be quadrant 1 because cosine's positive there. This 2 theta has to be in quadrant 2 because sine came out positive, cosine came out negative. And then you can use your tangent to confirm it. Yep, tangent's negative in quadrant 2 as well. So 2 theta is in quadrant 2. And it's just because whether those trig values came out positives or negatives. We are going to find the exact value of cosine of pi over 8. I want to find the exact value of cosine of pi over 8. Anytime you are asked for an exact value, that means you've somehow got to use the unit circle. So if we go to our unit circle, you are not going to see pi over 8 on there. Pi over 8 is not on here anywhere. So we've somehow got to use trig identities and some algebra to figure out how to make pi over 8. If you want to, if you're not good with fractions, you can change pi over 8 to a degree angle and go from there. That might be helpful. Pi over 8 is equivalent to 22.5 degrees. So that might be helpful, 22.5 degrees. 22.5 degrees is exactly half of 45. I just said the word half. That tells me I'm going to use a half angle identity. So, to find the cosine of pi over 8, I'm really going to do the cosine of pi over 4 cut in half. Pi over 8 is pi over 4 cut in half. So I'm going to use my half angle identity with pi over 4 plugged in. So the half angle identity for cosine is plus or minus square root. And remember, your half angle identities contain cosine x. And cosine to cosine, they match, so plus. And 1 and over 2. And we're going to plug pi over 4 in because we're doing half of pi over 4. And pi over 8 is in quadrant 1. So our answer is going to be positive. Cosine's positive in quadrant 1. So this is going to be positive square root of 1 plus cosine of pi over 4 all over 2. And we need to simplify as much as humanly possible. So look on your unit circle and see what the value for cosine of pi over 4 is. Cosine is the x, remember? So radical 2 over 2. We cannot leave it like that because we have a fraction inside of another fraction. That is bad. That's bad algebra. So we need to fix it. And the fastest way to fix that is to look at the denominator that's out of place, that's making this a fraction inside of a fraction, and multiply everything by it. So the one thing that's messing us up is the fact that there is this extra denominator here. If that wasn't there, we'd be fine. So what I'm going to do is I'm going to multiply in the top by 2. And since there's 2 terms, I'm going to have to distribute it. And I'm going to multiply in the bottom by 2. The reason I'm doing that is because when I multiply here by 2, I'm going to be multiplying by 2 and this divide by 2, they're going to cancel. And it's going to fix it. So I'm going to have the square root of 2 plus, here they cancel, radical 2 all over 4. One more thing to fix. This whole thing is under the square root, and one of those numbers is a perfect square, the 4. So technically that guy can come out, and we can just leave the top in the square root. So the square root of 2 plus radical 2 all over 2. Now that thing is hideous, but that's the exact value for cosine of pi over 8. So I want to do a couple of simplifying problems now. So these don't actually have values plugged in. And I know a few of you have expressed some concerns about using the identities for simplifying and for doing proofs. I am going to do another video for 7.3 that just deals with the proofs. So right now I just want to do some simplifying problems and how you know when to use which identities, how you know when to stop. Sometimes those are the hardest parts of these simplifying problems. So I'm just going to do a couple more, trying to keep this video under an hour. It's right about 42 minutes right now. So I'm going to do 2 more problems, and the directions here are just to simplify. And we want to simplify as much as possible. And the goals for simplifying trig expressions are to reduce the number of trig functions to as few as possible. Eliminate fractions when possible. And apply all possible identities, which is kind of a broad instruction, and it really requires you to be familiar with the identities to be able to recognize when you see a piece that can be replaced with an identity. And for a lot of these simplifying problems, don't forget algebra. There's always going to be some algebra to do. There's always going to be some multiplication or some division, things like that. Yes, this is trig class, so there's going to be some sort of trig to do, but there's also going to be some algebra to do. So the first one we're going to look at, we want to simplify 2 minus secant squared x all over secant squared x. 2 minus secant squared x all over secant squared x. Now, a lot of people would be tempted to just cancel those secant squared x and say the answer is 2, and that is not correct. You cannot cancel the secant squared x because of the subtraction. Those two terms are bound together. Anytime there is addition or subtraction, those two terms are bound and they have to stay together. What you can do, though, is you can divide them individually. Division and multiplication can be split up, but addition and subtraction cannot. So do not separate the subtraction. Don't try to cancel the secants because that secant is married to the 2 with the subtraction. But I can go ahead and divide them individually by secant squared. So this is just algebra, and that is an algebra rule. So this is 2 over secant squared minus secant squared over secant squared. And now that I have divided them individually, now there is no subtraction in that fraction, and now you can cancel. One of the things I said to do is eliminate fractions when possible. And there is a way for you to eliminate the fraction here using a trig identity. There is a way for you to pull secant up to the numerator. There is a different trig function that's equivalent to secant if you pull it up to the top. The reciprocal function for secant, which is cosine. So this is the same as 2 cosine squared x. And then my second term, secant squared over secant squared, is just equal to 1. So I've followed 2 of my rules so far. I've eliminated fractions when possible. I have also not forgotten about my algebra. This is where some people would be tempted to stop and they would not be sure what else to do. But we have not applied all possible trig identities. This is actually a trig identity. 2 cosine squared x minus 1 is a trig identity. And I'm going to scroll all the way back up here and show you where I talked about this about 15 or 20 minutes ago. 2 cosine squared x minus 1 and it's circled right there in red. 2 cosine squared x minus 1 is cosine of 2x. We want to do that because it simplifies our expression. It takes something that has 2 terms in it and it replaces it with something that only has 1 term. So that does simplify it. So reducing the number of terms, I should add that to my list, also helps to simplify. So this is cosine of 2x. So we also want to reduce the number of terms when possible. So 2 minus secant squared divided by secant squared, I started by separating. I used a trig identity to bring my secant squared up as a cosine squared. I just used some algebra to divide, and then I recognized that as a trig identity for cosine 2x. And there's nothing else that we can do from there. It's a single trig function. It's a single term. It can't get any simpler than that. So let me try one that's a little bit more difficult. Let's see. Yeah, you might think this one's a little bit difficult. Sine of pi over 2 minus x times secant x minus cosine x. We want to simplify that as much as possible. There are multiple things to do here. First of all, I've got 3 different trig functions: sine, secant, and cosine. Unless we absolutely have to, we don't ever want to leave 3 different trig functions in our answer. We want to simplify this down into as few trig functions as possible. Now, there might be a case where we have to leave it as 3 different trig functions, and if we have to, then that's fine. Another thing I'm seeing is that this angle has got an operation in it and these don't. So this is where I'm going to start. I'm going to apply, you've got a couple options. If you remember your cofunction identity and that is a cofunction identity, then you can use it. If you don't remember that it's a cofunction identity, you can always use your sum or difference identity. And I'm just going to pretend off the top that I don't remember my cofunction identity, and I'm just saying, oh, I see subtraction inside of an angle. I'm going to use my difference identity. I'm ignoring this one for now. I'm going to hold on to that for just a second, and I'm going to just work with my sine of pi over 2 minus x. So remember, sine is the nice guy. He's going to say, all right, I'm going to take on my first angle, let cosine take on the second angle. I'm going to keep the operation the same, and then I'll let cosine take on the first angle, and then I'll take on the second angle. Sine of pi over 2 is equal to 1. You can look that up on your unit circle. Cosine of pi over 2 is equal to 0, which means that whole second term is gone, because 0 times anything is 0. 1 times cosine x is just cosine x. This entire front piece just turns into cosine x. So now what I have is cosine x times secant x minus cosine x. Looking better already. So I'm going to do some algebra now. I'm just going to distribute. Cosine x times secant x minus cosine squared x. Okay, not too bad. I recognize something here. Cosine and secant are reciprocals of one another. So I'm not quite sure what to do with that yet, but I know secant is 1 over cosine. Well, cosine times 1 over cosine, that's cosine over cosine. Well, cosine over cosine is just 1. So this is just 1 minus cosine squared, which is great, but you're not done because that is a trig identity. So be really, really careful at your last step and make sure that you're not ending on a trig identity. 1 minus cosine squared is a trig identity back from section 7.1. I'm going to flip over to the 7.1 notes that I took when I made the 7.1 video. 1 minus cosine squared oh wow, these are so much neater. 1 minus cosine squared, there it is. 1 minus cosine squared is equal to sine squared. That's my final answer. I can't make it any simpler than that. It's only one trig function. One term, one trig function. Can't make it any simpler. So don't forget your algebra. Use individual little trig identities along the way. And then at the very end, always check and make sure that you're not ending with a trig identity and there's not one more thing that you could possibly do. So in 7.3, they're not just simplification problems, but they're proofs. And with the proofs, you've actually got two sides to your equation, and you're wanting to work it all the way down until both sides match. Now, this looks a little bit different on paper than it does in MyLabs Plus. So I'm going to do a couple on paper, but then I'm also going to go into MyLabs Plus and show you what MyLabs Plus wants you to do, because they kind of guide you along the way and then ask you what you're doing. And that's more like what you're doing in your homework and what you're going to do on your test. So I think it'll be a little bit more helpful if I do some MyLabs Plus problems in 7.3. I think that'll be more helpful for the test. So I will be making that 7.3 video shortly and pushing that out as well. And I hope this helps with your 7.2.